Hello, and welcome to a discussion on Subwar, the design and development, all about how to create a complex multiplayer skill for the Amazon Echo. This is Joseph Chiquinta from Zazazu presenting. So, what is Subwar? We had a number of objectives when we set down to produce Subwar. We really wanted to show and off the Alexa platform for what it was worth. So we decided what we had to do had to be significant and had to cover a number of areas. We wanted to create something interactive. A lot of skills out there are sort of one shot, you use them, they go away, simple things like that. We wanted a skill you talked to. You talked to it talked back, you had a conversation with it. And that's how you progress the logic of the skill. We wanted it to be multiplayer. Again, a lot of skills are just for the individual. You do your stuff as an individual. You might come back to it later or whatever. But there's millions of Echo users out there. And skills are by their nature client-server based. So there's no reason you can't interact with your Echo and through that interact with other people in this huge community out there. So we wanted something that was multiplayer and took advantage of that. We wanted it to be a game. We wanted to engage people. We wanted to show that this can be a gaming platform. We wanted it to be audio only. We didn't want it to be an adjunct to some piece of hardware. We didn't want it to be an adjunct to some website out there that offered some service, and this was just another way of getting to that. It's just not an API that this serves up another thing for. We wanted this to be the start and finish of it all, that you only interacted through it this way. So it's not playing second fiddle to anyone. So where was the inspiration from all of this? Well, first of all, we wanted to do some sort of entry for the Hackster.io competition. We're the people who created Starlanes, the massively multiplayer online game for Alexa. Biggest, some people called it the most comprehensive skill, advanced skill out there for Alexa. You have to make your own mind up there. But we wanted to do something like that. And since it was going to be released into the public domain, we couldn't really do anything with Starlanes itself. That's our premier skill, and we have all sorts of great plans for that. But we really want to see more things like that on the Alexa platform. There's plenty of room out there. This is not a competition. So we wanted to produce something, since we're going to release it to the public domain anyways, that other people could use to show off the power that Alexa has as a games platform and give people a leg up into creating their own things. It's released under the Apache license. It's a project up on GitHub. Once the competition closes, we're going to open it up. We're going to accept contributions from other people to help improve the game, do more stuff with it. It'll also be there for you to clone and use as a basis for making your own games. You can take our tips and techniques if you like them. You can take our code if you like that. You can produce your own stuff with it. Now we will have a lovely demo.
Alexa, open Subwar.
Attention. Captain on deck. Welcome, sir. I am Lieutenant Alexa, your first officer. Are you ready to hunt some submarines?
Yes.
We've launched. The Boston is 2 kilometers north of the Strait's midpoint. We are just at the surface. We have a full complement of 6 torpedoes. Try giving an order to move, fire, listen, or ping the sonar.
South.
The Boston is 1 kilometers north of the Strait's midpoint. We are just at the surface. What are your orders now?
South.
The Boston is in the exact midpoint of the Straits. We are just at the surface. What are your orders now?
Listen.
Silent running, sir. Someone else is pinging us northeast at about 5 kilometers and slightly below us. Something just exploded north-northwest at about 4 kilometers. What next?
Dive.
The Boston is in the exact midpoint of the Straits. We are 100 meters below the surface. What are your orders now?
Listen.
Silent running, sir. Nothing heard. Captain Joe. What next?
Ping.
Pinging sonar, sir. Our sonar here signal returns north-northeast at about 5 kilometers, north-northwest at about 3 kilometers, and north at about 4 kilometers. Someone else is pinging us north-northeast at about 5 kilometers. What next?
North.
The Boston is 1 kilometers north of the strait's midpoint. We are 100 meters below the surface. Someone else is pinging us north-northwest at about 3 kilometers. Something just exploded north-northwest at about 3 kilometers. What are your orders now?
North.
The Boston is 2 kilometers north of the strait's midpoint. We are 100 meters below the surface. What are your orders now?
Listen.
Silent running, sir. We can hear a ship's screw northeast at about 1 kilometers. Someone else is pinging us northwest at about 1 kilometers. What next?
Fire west.
Torpedo away, Captain Joe. Direct hit. What are your orders now?
Yes. Listen.
Silent running, sir.
Wasn't that a lovely demo? So, the rest of this presentation, we're going to go over how we developed Subwar. There's a number of aspects to cover. Very briefly, there's audio design, something people frequently neglect, that it's a very different sort of thing to develop under. So there's a lot of aspects you really have to think about when you're designing how somebody interacts with you with voice only. We're going to talk a bit about how we chose the platform, what language we chose, why we chose that, how that influences what you might choose. We're going to go through the architecture of the application, why we laid it out the way we did, how you might take advantage of that in designing your own applications. We're going to cover the development, the tools we used, how we did it, how we uploaded it, and the testing and support. A lot of people frequently focus on just the coding, and that's great if you're a coder, but if you really want to be successful, you have to think like a software engineer. That's looking at the full life cycle of the product, not just writing the code, but the usability, the testability, the maintainability, all that sort of stuff. So we're going to go over some of the aspects we used for that, try to give some suggestions to people that they can use for their own projects. So let's start with design. Shout out to Eric and his Derp group who wrote a blog post about the 10 commandments of Alexa development, where you've got a similar one, sort of as a salute to him with the 10 commandments of Alexa design. Number 1 on our list of 10 commandments is design before you develop. It's really, you just don't want to jump in and start writing code. You can kind of get away with that when you're doing visual stuff for GUI programming, because you can do a bit of it here, a bit of it there, and you can develop the program in parallel with how a user experiences it. Audio applications are not linear in the same sense. At any point, you can invoke any of the commands that can possibly be done. So it's more like a matrix than a line, and you really have to think about it before you do it. And it helps you an awful lot if you start there. But how do you start that? It starts with a conversation. You want to sit down without any technical stuff around you, no computer, no nothing, just sit down and think, how would I talk to it? What would it say back to me? Start creating the conversation. Come up with a whole library of conversations. Like, well, I'd say, hey Alexa, let's play Subwar. And it would say something back. And you would write that down. Sit there, pen and paper, keyboard type or whatever. Work out what those conversations are. Forget about the technical limitations. In fact, this exercise is best done by somebody who is not technical at all. Just somebody who's an enthusiast, likes the concept, doesn't know what Echo can't do. Because if you are sitting there and like, oh my God, I have to write the code for this, you're going to limit yourself. Okay, you don't want that. You want an interface that's natural. That's the person talking to the Echo. You want to sit down and say, okay, well, what's their ideal experience? They say this, the Echo says this, you say this, it responds with this. Chronicle all of that. Come up with several conversations. If there's one sort of feature and you can perhaps access it in different ways, or it replies in different ways at different times, come up with it. Come up with several conversations. You can see how we took this approach with Subwar. It's all up there on the wiki. You can see the conversations we started with. And that is the first thing we did. We sat down and said, okay, how are we going to talk to this? How are we going to play this game? By talking to it. And that's your starting point. Once you have those conversations, you can start to refine them. Because again, you can't, there's certain things you just can't do with Alexa. So you do have to eventually take technical limitations to account. But you don't want to start with those limitations. You want to come to those limitations. You may find that you can actually address some stuff. When you're designing for the mobile platform, it's a good background for doing this sort of thing. Because the real big difference with designing for mobile is that you've only got so much screen real estate. You've got to really be minimalist. You've got to really be design and usability focused. It's a very similar sort of thing for audio design. It's not that you don't have a limited screen space. The user can say anything, and that's a great flexibility, but you can't say too much. All right? If you've used Echo at any length of time, once it goes on for more than a sentence or two, you kind of forget the first sentence. And you have to say, okay, what was that again? It's like, okay, what's the weather? And it tells you the weather. And you go, okay, wait. What was the temperature? I know if it's going to rain. Now, what's the temperature? And you have to go back and keep it short. It's better to have more small interactions than long ones. Make it a conversation. Hey, Alexa, you ask something, it gives you an answer back. You ask something else, you get an answer back. Instead of asking one thing and getting a whole data dump of results. That's the web page approach. This is not a browser. This is a conversation. Another way to refine your choices is to take your conversations and kind of shuffle them up. Put each exchange on a card. Take them, shuffle them up, mix them around. Because a user can say anything in any order. And you might flip through them and say, oh, well, okay, they just said this, now they're saying this. That doesn't really make sense in this context. Or maybe it could make sense in this context. Okay, you might discover that, oh, okay, I can respond to the user in different ways in different places. This is how you start to get an understanding for the contexts of your application. That on a GUI, you might have different screens that do different things. In an audio app, you're going to have different contexts. The same questions might have different answers in different contexts. Then you want to go through and simplify things, okay? More than likely, you've kind of rambled on as you've created these conversations. You want to look for commonalities. You want to work out, okay, well, this is the same here and this is the same here. Let's merge those together. Wherever possible, you want to use the default intents that Amazon supply. They have standards like yes, no, cancel, start over, things like that. If you can kind of map some of your responses to those, that's pretty good. Because it's just like in Windows development, there's certain standard dialog boxes that come up, the abort, retry, cancel dialog box, something like that. In Alexa skills, these default responses are common to all skills. So as a user is trained in one skill, you can leverage that training in your own skill by reusing those common answers. So taking that advice, let's look at some specific examples we came across while refining Subwars. Okay, so our first draft, we wanted to have a leaderboard. We wanted to give players incentives to have high skill scores. We wanted to directly contrast their playing with other people. So we said, we want a leaderboard. So we first looked at this. We're thinking it's like, well, let's look at all these other games. What do they have? We're going to have subs. They're going to be shooting each other. We can rank players based on the number of kills they've made. How many subs have they sunk? The higher they are up that leaderboard. We could have more than one leaderboard. We have another one saying, okay, how accurate are they? If they used 300 torpedoes and sank 3 ships, well, that's not so good. If they use 6 torpedoes and sank 3 ships, that's better. So we can rank them based on how accurate they've been. Give people an incentive to, sort of not just shoot off ammunition left, right, and center. Another way would be the average game score. How consistently good are you? We thought these are all good things. Is this good feedback to give somebody? Let's do that. So we started that with that in mind. Then we started creating sample conversations. And it got to the point where it's like, man, this is a lot of, how do we tell the user this? How do we get them to choose what leaderboard they want to hear about? Okay, it just this gets more complex and harder for the user to use than really the value that's added. So we said, okay, let's just have one leaderboard. You say leaderboard, you get total rank by total kills. Okay, the other ones are kind of nice, but really, it wasn't worth the complexity. So we used that, we refined it, we cut our original idea from what we could do to what we should do. And that's the kind of thing you should keep in mind when looking at refinements. Okay, another thing is like, we wanted to have a bunch of things. We wanted to have, there's certain commands you have. There's not a lot of them, but there's a certain amount of them. We also wanted you to be able to customize. We wanted to be able to give your name. So instead of saying, well, Captain, you're about to launch, it would say, well, Captain Diana, time to launch. It's time to launch the SS Lollipop. Okay, you can name your ship. But our first draft, it's like, okay, as soon as they start, before they can get to the game, they have to listen to all this stuff about how to play the game. And we've already talked about long-winded responses. By the time you get to the third one, you've forgotten the first one. So we're like, we can't have that. So instead, we sort of said, okay, how do we quickly get the person to playing? So let's give them, the first time they invoke the skill, the minimum information they need to be able to play the skill. Now, the next time they come back to the skill, they like it, they'll come back. The next time they come back to the skill, let's give them a little more information, or let's give them different information. So the idea is that we broke the learning stuff, the discoverability over several sessions, engaging with the content. Okay, each time they hear a little bit of different stuff, they learn new things. It's kind of like tip of the day, that sort of thing. With that, we were able to keep those customization features in there that we wanted to keep, but originally could not find a way to do cumbersome. So now you have all your conversations, you've kind of refined them a bit. How do you turn that into an interaction model? Amazon has a very specific interaction model. A lot of people find it kind of constrictive, but in all honesty, what they're going for is the highest accuracy rate possible. And I agree with that logic. The higher the accuracy that Alexa understands you with, the more usable your skill is going to be. So you need to deal with the fact that it's kind of restrictive. You need to work with that, not try to defeat it, and produce something into their model. So you have to take then all of these chatty responses you have to and from the user and digest them down into the intents that it needs. These are kind of like your function calls. First thing you do is group everything where you have an identical input. If you say yes here and you say yes over there, well, that's going to be the same intent. And if you say sure over here and something else over here, or even more like launch torpedoes, fire torpedoes, or attack, these sort of things, it's like, yeah, they're actually underneath the covers. They're going to be done the same. Let's group them together. Okay, so that's your first pass of working out how to take all of these responses and turn them into intents. The second pass is you're going to look at the groups that you have and decide, are these groups really the same, but for one of the sort of things you say, like move north and move south. Well, those could be seen as being the same thing, but with a different direct object. Okay, if you look at it as the intent is the verb and the subject matter is the direct object. So what you're going to want to do is then coalesce those groups together and differentiate them by considering that difference to be a slot. So you have the slots for the intents. And that's how Alexa derives its interaction model. It needs slots, it needs intents, and then it needs slots for those intents. And that's how you go from having a conversational thing, a purely abstract, non-technical generated conversation, into something you can implement. So, to cover that all over again, the steps we took: map out the conversations, chronicle that, get somebody to come up with all the ways you want to talk to it. You want to then take them, bring some regularity to that, refine them, work out the things that are, this is just way too specific, or this is way too cumbersome, nobody's going to listen to that much. Condense it down. And then lastly, take that and create an interaction model from it. Break it down, group things together, isolate them until you have your intents and your slots. And then you're ready to implement. Okay, so now we're ready to think about coding. First thing you have to choose is what platform you want to deploy this on, because that influences all the rest of your decisions. Now, we chose to stick with the Amazon ecosystem. We said, okay, whatever we do, we want it to be something that Amazon provides. Okay, that can be a good business decision if you're already an Amazon customer, or if you want to later resell your application to another party. If everything's all up there on Amazon, it kind of keeps it all together. In our case, it was more, that we want other people to use this. Amazon's kind of the common denominator. If we sort of spun up our own little custom solution, then other people would have to do that. That doesn't make a good example. So that influenced our decision. Your mileage may vary. you may want to do something a little bit different. For persistence, we needed persistence so we could do the leaderboard. We chose Dynamo.io because that is a service provided by Amazon. It's their kind of NoSQL database. If you don't like NoSQL bases or you're more familiar with relational databases, you could have used a relational database. It doesn't really matter much. The persistent requirements for this weren't very high, so, that was an easy choice. Now, when we looked at deployment choices, we chose to use servlets on Amazon Elastic Beanstalk. Okay, they're scalable because everything Amazon does is scalable. They have a fully featured DevOps interface, which again, most stuff on AWS does, but this goes all the way down to the application level instead of like a machine level. And the people working on it were familiar with this. Okay, that's always a consideration. Other things you could look at, and we looked at and chose not to, was the Lambda service. I know the competition very much encouraged people to use Lambda, but one of the limitations of Lambda is you can't cache objects and you can't run stuff in the background. Okay, they're all single instance, it's invoked, and then it goes away. Poof. And that adds a lot of extra pressure to your synchronization stuff, or rather all that saving you. If you want to save and persist stuff, you have to do that while the user is waiting. You can't put it in the background. Similarly, if you have to load it in, you can't cache it. You have to load it in while the user is waiting. We didn't want to go there. It just adds too much to it. It's also going to be a lot harder to do sort of live real-time interactivity between players when your VM goes away between invocations. EC2 is kind of on the other end of the spectrum. That's where you have a whole server. Elastic Beanstalk's kind of in the middle. It runs Tomcat. You can put your servlets on Tomcat. EC2, you got a machine. You can put whatever you want on it. That's a good choice if you go the non-servlet route. If you want to run your own server, put your own, like Python or Node.js engine on it, EC2 is great because you can do whatever you want there. If you have customized backend stuff, that works great there. Didn't really fit into what we were doing here, but it's not necessarily a bad choice if you're going in a different direction. For our development language, we chose Java. It's one of the 3 supported SDKs for Alexa. There are plenty of other SDKs in other languages, but for an example, we really wanted to stick to something that Amazon itself supported. For downwards maintainability, that's not a bad choice to keep in mind. It's a fully featured, strictly typed language. We like strict typing. Alexa is kind of a weird weird debugging and execution environment because you're running it on a server somewhere, but it's being called indirectly through another process. It's hard enough to debug as it is. We really liked having a strictly typed language because all those little syntax errors and stuff like that are much easier to catch earlier rather than later. And again, our staff was familiar with Java. More so than the other languages, so that factored into it. The other 2 supported languages are Node.js. That is very good for what it was designed for, which is like quick, server invocations where you don't want threads to block each other. But the callback model it uses to achieve that, it gets kind of cranky at high complexity. It just becomes very cumbersome to write in. So we didn't want to use it and ignore that feature because that's what it's designed for. But if we use that feature, it added more to the complexity that was there, so we decided not to. Python, again, that Python is, it's a fully featured language, but it is loosely typed. It is a lot of bugs you don't find till runtime rather than compile time, and that's something that we wanted in our thing. Again, your choices may vary. These are not sort of lie down on the track site. This is the only way to do it. Really, you got to look at what you got. So, overall, you got to make your choices. This is how we made our choices about our stuff. It's going to be different from you. The overall thing I would say, familiarity trumps functionality. Okay? If you really, really like Python, you can get it to work in Python. Don't kill yourself to write it in Java just because we wrote it in Java. If you really like Node.js, you really like JavaScript, do it in that. You'll find a way to do it. If you're good at it, you'll find a way to do it. Alexa's weird and different. There are a lot of things you're going to learn. Audio programming, audio design is weird and different. Pick something. If you have your choice of programming languages, pick something you already know. Make it easy for yourself. Don't try to learn a whole bunch of things at once. So, program architecture. The idea of dividing things into layers has been around for a very long time. Usually there's like these 7 canonical layers, and application development, it's a little different from Alexa. we have our own layering system, and we'll go into that. Advantages to using layers. You can create a single point of entry for each of the layers so that all the layers funnel through one little invocation to the next layer, and so on and so forth down. This adds to flexibility. As you'll see, keeping the different logic layers separate allow you to different deployment models in the future. If you want to do it on something other than Alexa, or you want to do it maybe actually have a multi-client app that has like a web interface or has some other sort of thing, breaking it into layers leaves that option open going forward. By breaking into layers, each part solves one problem. Okay, we're going to do the audio stuff here. We're going to do the game stuff here. That means each in turn is going to be simpler than if you tried to do it all together. Yeah, you may have more code because you got to have the different layers and you do each thing in each layer, but those layers individually are going to be simpler. It goes back to the whole software engineering, maintainability. You could do it more optimally if you mashed it all together, but you're going to come back to it in 6 months and you're like, what was I doing? Keep it simple. The other advantage is each layer can be tested separately. We'll come to this more when we talk about testing, but that is of immeasurable benefit. You can isolate your bugs to different parts of the stack. So the lowest layer from our consideration is the game layer. Okay, this is where we put all the game logic. At this point, we're just working about what are the rules of the game, how do we enforce those rules, how do we synchronize it so that multiple players acting at the same time in the same environment is all thread safe and nobody steps on each other's toes, and when there's things happening near simultaneously, it works out right. Okay, we can put that all in here. We're not even going to think about what this looks like. We're not even going to think how people articulate their commands. It's just we're going to deal with them as the abstract. A command comes in to fire a torpedo from this player. Let's go work out what happens. Make sure we do the right thing so that when the next player comes in, they can see the results of what happened. This is also where we put the AI logic. AI players don't communicate through the user interface. They communicate at this level at the game layer. That way, you have the same logic applies no matter how you want to surface it. They say you create a graphical user interface layer, the rules are going to be the same because they're down here in this layer before where we're not even taking care of that. This is also where we put in the persistence. If we're going to save something to disk, this is where we save it. The other advantage of having a single point of entry or at this level is you can secure it against hacking. And by hacking, I don't necessarily mean an evil person coming in and trying to get at your site, but also players are players. This is a game. People want to win. They're going to try to work out how to game the system. So being able to have one point where you cater for that is very advantageous. It all goes through the game's logic. On top of this, we build our second layer, the audio layer. Okay, this, at a primary level, translates audio input and output into game mechanics. Okay, somebody says something, it's like, okay, let's do this and let's work out what game command that is. And the game command does something, it tells you its new state. You've got to turn that into some sort of descriptive output, saying, oh, put in sound saying, whoosh, there goes your torpedo, boom, it exploded, things like that. The thing to remember is this is not as trivial as it sounds. This is not a one-to-one map. When we refined our audio interface, we sort of came up with the idea of like, okay, well, we need a pre-game area context, and we need a game context. So it's the idea that, okay, I haven't started the game yet. I can ask it for help. I can ask it about information. I can look at the leaderboard. I can name my ship. I can do stuff like that. Oh, now I'm going to start a game. Now I'm in the game context. I'm moving around. I'm firing torpedoes. I'm pinging my sonar. That's in the game context. Oh, I got blown up. I get knocked back into the pre-game context. Now, in that thing, since there's no actual game interaction in the pre-game area, there's nothing in the games layer about that because there's no game logic happening. That's all in the audio layer. That's where we manage the audio state and work out where the player is there, give them the help information and stuff like that. So that's important to remember that there is different things in these different layers. It's not just a simple, simplistic pass-through up and down. Now, the audio layer is very specifically the audio layer. The next layer is the Alexa layer, and we keep them separate so that we don't have in the audio layer any Alexa specifics. If we want to do some other audio interface later, we can put that on top at this layer here. And the game kind of sounds the same for both of them, but here it's coming out of the Echo, over there it's coming out of, I don't know, Siri, Cortana, OK Google, whatever. Whenever somebody opens their API, you'll have that as an option. So that leaves the Alexa layer. This is the very topmost layer in the Alexa world. And really all it does is translates from Alexa objects into our objects, our audio layer objects, okay? From one to the other and from the other back to the one again. This is, again, protects our code from changes. Say Alexa changed some of their interface. All we need to do is change their changes in this layer here. We don't have to go deep down into our program logic to change that stuff here. We just need to change how it interfaces this way and that way. So, we've got our design, we've got our architecture, actual development. And again, this is going to depend on your choices of platform and so forth, but for us, using Java as a servlet, we use the Eclipse IDE with the AWS plugin. You know, there's a lot of different ways you can do that. Again, this was mostly staff familiarity here. You know, we knew how to use this. Let's just go with what we know, not pile up too many things. You want to use IntelliJ, NetBeans, whatever. Anything AWS supports, you know, go for it. It doesn't matter. We used GitHub for source control. In retrospect, you know, we might have Amazon also have their source control system, but since this was a sample and, you know, people are more familiar with GitHub for samples, we put our stuff up on there. Now, we just didn't use it for source control. We also used it for project management. Okay, we made an extensive use of the issue tracker there, and you can go and look at the project and you can see all the issues. We broke them into milestones, you know, set our goals, knock down our goals. Definitely every time we checked in and against the issue so that you can tie in the individual issue and you can see the code changes that were made to service that. And again, some of that was, we're doing this in the public eye. We want people to see good software practices, not just good development, but the overall project management. So those are some of the tools we used for that. Now, when you're deploying a skill to Alexa, there are a number of steps, especially if you are producing a servlet. You got to take the servlet, you got to build a WAR file, you got to upload that to your Elastic Beanstalk server, and there's a number of different steps. We wrapped all those steps together into a sort of, you know, actually we wrote a little tool to bind them all together, and also because this is also being maintained with several of our other skills, it's part of our sort of, you know, in-house development lifecycle to wrap it all together. So it goes through these steps that we list here. You know, first we build our WAR file. It contains the servlet. That can be done in an automated way. Then we upload this to S3. Now, you can just upload it directly to the thing, but then your skill comes down, it uploads it all, and the skill comes up again. Your players are experiencing downtime. And since once it's out there, everybody's using it, we wanted to have a much better experience. So if we upload it first to S3, which, if I haven't explained, is Amazon's cloud storage mechanism, then we're ready to deploy it, but it hasn't been deployed yet. So we then wait, and we can ping the skill and see if there's still players playing it. If there's players currently in the middle of the game, we want to wait. You know, if it gets so high that we're waiting forever, that's a problem. But right now, we're going to wait until there's no active players. Let's say, okay. Then we're going to go and switch the proxy into maintenance mode. Now, our skill doesn't talk directly to our servlet. It talks to a Lambda proxy, and that proxy then talks to our servlet. Mostly we do this to get around the whole SSL certificate thing, because that's a real pain in the neck to do in Alexa. And it's just easier to talk to Lambda. Lambda talks to the servlet. There's no real impact on performance, so we're happy with that. Now, it also gives us the advantage here that normally the proxy just, you know, receives the request from Alexa, calls out to the servlet. Well, we actually have a different mode in there, so if a switch is flipped, instead it says, oh, I'm sorry, Subwar is in maintenance mode right now. Please try again in 5 minutes. So at this point, we flip that switch, so the players experience no downtime, they just get this message, it gracefully degrades, giving a message saying it's undergoing maintenance. Now, we copy the WAR file from S3 to the server, and that's much quicker than uploading it directly to the server. So we get that, kick it off, wait till we see all green lines so we know it's up and running, and then we switch the proxy back. So this type of setup minimizes downtime for the players because we copy it all up to S3 first, and it also gives them a graceful degradation. Like they go and they try to play it in the middle of maintenance, and instead of saying your skill can't be reached or whatever the canned message is, you get a much nicer message saying, explaining what's going on and asking them to come back later. You know, it's a bit of investment to get this all working, but there's lots of DevOps commands that AWS provides that helps you getting over it. And overall, if you're doing a serious skill and you want to provide good user service, this is a very good thing to follow. Testing! That what every programmer loves to do. No, seriously. It's back to the whole lecture on software engineering. It's vital. You don't want your users finding bugs. You want to find bugs. It's not a fault when you find a bug. It's a relief. It's another thing that your user is not going to experience. So we're very, very pro testing. For this, we used JUnit as our testing harness. Since we're doing it in Java, we have it there. We use JUnit. The tests we wrote are included with the project. You can see them right there. You can run them yourself. You can see how it was done. One nifty thing here is that given we have these layers, we're able to test these layers in isolation. We can just run it in our development environment. We don't have to put it up onto a servlet and go through all the process of redoing the code every time we want to test to see if something works. We can test the game layer, we can test the audio layer directly with function calls. That also means they run really fast, so you can do them all the time, not just before check-in. The unit tests we've written, we wrote some functional unit tests that test each area as we did it. For other things, we followed the conversations. Remember, in our audio design, we came up with these canonical conversations. Several of our unit tests look just like our conversations. We're saying, okay, if this is what a user is going to do, let's test this. In fact, that formed the basis of doing a certain amount of test-driven development. This is kind of a fashionable buzzword, but it's not applicable everywhere. There's plenty of criticisms of it, quite rightly. But for something like this, you really can do that. We sat down and said, okay, now that I've defined my interface, I'm going to write a test that walks through this conversation. Let's run it. What breaks? Okay, go fix that. Run it again. What breaks now? Let's go fix that. You can do that, and this is how, when it runs, you know that you now have all the logic there to do your conversation. That's very handy, and in fact, you can see one of the tests we did actually randomly calls the entry point for these APIs. It's like, okay, let's call a random audio thing, because a user can, in theory, do that. An audio interface, they can invoke any function at any time. So we just wrote a test that went through 1,000 iterations and just randomly calling things. And we made sure that it responded coherently, that it said something, even if it was like, that doesn't make any sense. That's fine. Okay. It means we handled it. We had something there. Because believe me, the CERT team will do that. But this then could rigorously do it and proof it all out. It can prove certain things like, yes, we always have a response. We're always setting the reprompt message. And we can enforce various things, make sure there's no exception throws. That should never happen. And by doing that sort of, random throw anything at the wall, we found a bunch of bugs that way. You can go look at the source code history, the check-in stuff. You can see when we wrote that test what we found doing that. Support. You're going to ship what you do someday, okay? And users are going to use it. And they're going to have problems, okay? And you're going to want to work out, like, why is it doing this? What's going on here? It's like, blah, 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 like that. So it's important when you write your code to think about that. To think about, okay, when I'm in the middle and I got users screaming at me because it's not working, or that, they had this great high score and now it's tanked for some reason, why did that happen? You can't single step through your code when it's up there on a server in a live situation. Think about that in advance. Put in debugging messages. We have that here. Log everything. And if you had to put in a debug message to debug a problem you had while developing it, leave it there. You might need it live. Now, this is not to say you want to completely spam your log file full of stuff. Use, Apache logging. Use some sort of thing that lets you filter out messages. Then you can turn it off for production, and then if you need to, just by resetting a environment variable, crank it up to a higher level, helps you diagnose your problem without having to redeploy the code. In Subwar, each layer produced its own debugging stuff, but it also provided a hook that you could hook the listen into that. And what we do is each of the higher levels hooks into the next down lower level and sort of bubbles its messages up all the way to the servlet level, where it hooks into the Alexa layer and thereby hooks into all the messages and spools them into a separate buffer. Now, normally, a Alexa skilled is called by sending a post message to a HTTP address. Well, we also, on that servlet, responded to the get HTTP method. And when that happens, we give it back the debug log. So it gives us a way to dynamically look at what's going on and see who's using the skill, what's happening there, were there any error messages that were caught and trapped, and what is the user experience. You can also, some of our other skills, Starlanes will persist this to log files, or rather it produces it in DynamoDB, things like that. Another side thing, that's a tip that's handy here, is that when you're persisting stuff to Dynamo, you can actually go into the separate interface and edit things directly there. That's kind of handy if a user experiences a problem or you want to sort something out, you can do it there. The trouble is if your application is caching that information, which A, is very highly recommended because that makes your application more responsive. B, you're charged for Dynamo and you're charged per access, a certain nominal amount. If you can cut that down by caching, it'll save you, a couple of pennies on your next bill. So do that, but in order for it to be able to uptake those changes you make, have another entry point on your servlet that just flushes the in-memory cache. That way you can make your change to DynamoDB, you can come back, hit that endpoint, and it flushes your cache. You're good to go again. So, going over the development stuff again. Have a bunch of layers. Do that each. It keeps each layer simple. You can test layer by layer. This is advantageous. You can finish one before moving on to the next one. If you've got problems, you can isolate them down to a specific layer. Anytime you find a problem, write a test. Alexa, put it in the top layer, isolate the Alexa specifics in that layer. If they change things, you can adapt to those changes without screwing up your code base. And once you've got that, once you've got your structure there, you're translating out of Alexa apps into your objects into your own objects. Everything else is just a coding exercise. Just write code. We presume you're coming into this, you know how to write code. You're now in your own domain. You don't have to worry about, how does this work for Alexa, et cetera, like that. Keeping that there, containing it in that area and then turning everything else into your own terms, you can just write code. So, thank you for listening to this presentation. I hope that was informative. There are a number of resources here. You can go look at the project on GitHub. Check it out. Do whatever you want with it. If you want to follow us, the Zazazoo website is linked there. And we have the LinkedIn profiles of a couple of people involved with this. So have fun and good luck with your own code.